Brandon.
Yeah, probably less than me.
They were nice people.
Exactly.
So if we have parties more often.
More seats.
More seats, Sergi.
More
No,
seats.
it's okay.
Better.
Sergi, we're going to impeach you in the hall chair unless you sit over here.
That involves one less person doing the work.
That's true. We're just going to make you the bitch hall chair.
We're gonna impeach ourselves as hall chair.
Yeah.
Okay, is everything good?
What if we put this back in?
If it doesn't project, that's fine. It's okay, I'll skip the Python. I don't want to do it anyway. Hope so. It was charged, right? Yeah, okay. All right. Hi, everyone.
Hello.
I'm Victor. My full name is Victor Costin. I'm a third-year PhD student. I'm in CSAIL, and I work in systems. I do mostly security in distributed systems, and I'll be your algorithms TA for this term. Yay! How many people went to lecture yesterday? All right. Are there any parts of the lecture that were particularly unclear that you guys want to go over? So that I schedule what I talk about in such a way that I'll cover that more than the parts that are boring and obvious.
Can you explain the complexity equations? Because I took O42 like 3 years ago.
Okay. What else? Thank you.
Maybe some basic outlines for like writing proofs relevant to like diffuse sets.
All right.
Like what sort of methodology?
Okay. Anything else? Okay, we're going to get started then. So the hardest and I think most important part of the whole course is learning how to deal with asymptotic complexity. So asymptotic complexity is this very nice tool where you have a function that looks like this, x plus, what do I have here, 10 plus sine. So you have this guy, which is quite long and horrible and would make your life miserable if you'd have to reason about it. And you can say that this is theta of n squared. X, sorry. So everything that's here goes away, and this constant factor here goes away, and it's a nice and small function. Why is that the case, first of all? If I plot this function, and since I don't have my projector, you'll have to take my word for it, I will get something that looks like this. If I plot this function, I will get something that looks like this. This is a scale from 0 to 200. However, if I make my scale 0 to 20,000, let's say 200,000 to make sure that it's going to be correct, x squared looks like this, and this function looks like this. And as you make the scale bigger and bigger, you can't even see this noise anymore. The reason is that all the noise is in this term, in the x to the power of 1/5 term. And as n, pretend this is n, xn, same thing. So as the input to the function gets bigger and bigger, this grows at a much faster rate than this. So if what I care about is how the function grows, I can ignore anything aside from the dominant term. Do people remember this from lecture? Does this make sense? OK, if it doesn't, that's great. It means that I'm not wasting time covering it. So we learned about 3 symbols, or we will learn about 3 symbols when talking about asymptotic complexity. The 3 symbols are theta, O, and omega. Let's say this complicated function is g, and this nice simple function is f. If I say that g of x is theta of f of x, that means 2 things. It means I have a lower bound, like I showed here, and the lower bound looks something like x squared. And it means that I also have an upper bound for it that also looks like x squared. So the upper bound would be something like this. And if I say this, then I'm making a promise that the function stays between the lower bound and the upper bound, and the bounds look sort of the same. I can't really have x squared here and x squared here, right? That would be impossible. So that's why I said they look the same. They're not the same. And they're not the same because they're allowed to differ by a constant factor. So if this is f, and say this is f prime, f of x might be x squared. And we know for sure that this is going to be lower than this. And f prime of x might be 1.2 times x squared. And because I have a 1.1 here, and I know that these get smaller and smaller in relation to this as the function, as the inputs to the function get bigger, I know that this is going to be the dominating factor. And because this is bigger than this function is going to eventually be larger than this function. So I have a bound from above, and I have a bound from below. And the bounds look almost the same. They're only different by a constant factor. This is theta. To make things spicier, by the way, theta is really hard to pronounce as opposed to O. So we usually say and write O instead of theta. We'll talk about what O really means in a bit. But if you see O in a lot of places, including our notes, know that most of the time we actually mean theta. And sorry for that.
When do we know we actually mean O?
You can ask us and we'll tell you. Fortunately, it doesn't matter too much. So we're trying to get an idea of how the functions look like in the bigger picture. So most of the time, it doesn't matter. I'll give you an example, though, of where it matters and how it could matter. So suppose I have another function that looks like, that looks like this. So this is kind of ugly, too. This function is g of x, say x times 1 plus sine of x. So I can't say anything about the lower bound of this. This is going to hit 0 at an infinite number of values, right? So I can't say that. I can't have a nice lower bound for it. The lower bound for it is 0. But I'm pretty sure that it's never going to be bigger than 2x, right? And that's still worth something. So there's this other function here that's supposed to be a line. Pretend it's a line. F of x equals 2x. And I know for sure that this is never going to exceed this. And in that case, where I only have one upper bound and I don't have a good lower bound, I say that g of x is order of f of x. And this is what O really means. It means I only have an upper bound and not a lower bound. In most of the cases, when you're coding something, you don't really care how well your program can run if you're really lucky. What you really care about is how does it run in the worst case. or how does it run most of the time? So suppose you're Google and you're writing your search engine. You have to return a result to the user in 200 milliseconds because they did a study that shows that if you return the result in 400 milliseconds, they lose some number of users, which means they lose some number of billions a year. So to them, a guarantee that their algorithms complete in 200 milliseconds is pretty important because it means a ton of money. So if you have a running time that looks like this, that's okay, as long as this is 200 milliseconds for the number of pages that Google indexes. Does that make sense? Okay, no answer means yes. So if it doesn't make sense, please say something. Okay, I will draw another function. Again, wavy.
It
Yes.
says x times 1 plus something times. So what?
So it's
Oh, it's sine
1
of
plus
that.
sine of x.
It
it-
looks like the.
Yeah. Sorry, my handwriting is not very good. Well,
Well,
It doesn't really matter what it is. It just needs to be signed so that it looks wavy like this, so that I can make something that looks complicated.
okay, got it.
So in the first example, is it 1.2 times x squared?
Yes, I wanted something that's higher than 1.1.
Okay,
So
it's like time, not cost.
yes. Okay, now that I got a break, does anyone else want to ask questions? Okay. So I'm going to draw another function. This one looks like this. And this is f of x equals 1 plus sine of x. I have to use these signs to make them look like that. Times x to the power of, what do I have there? 1, 5 plus x to the power of 1/4. So for this function, I know for sure that it is greater than x to the power of 1/4, right? So if this is I know for sure that it's greater than that. Also, if I look at this, and I know that sine is never bigger than 1, I know this whole thing is going to be at most 2. So if I have another function that says f prime of x equals, say, 3 times x to the power of 1.5, I know that it's going to bound it from above. So I have two bounds. So it sort of looks like this case. Except when I use theta, I have to make sure that the bounds are very similar. They can only differ by a constant factor. In this case, my bounds differ by the exponent here, which is more than a constant factor, so they're not the same. So if I take my function, which by the way is g, if I want to say that g to the x is theta of something, I can't. Because no matter what I put in here, it's not going to be correct. The lower bound is this, the upper bound is this. But what I can do is I can say that I know for sure that it is theta of x to the power of 1/4. And by the way, I can also say that it is order of x to the power of 1/5. So if you have weird running times that look like this, then you can only use O and omega. And with that being said, we will use O for pretty much the rest of this course, and for most of the cases, we will use it to mean theta. Oh, by the way, these formulas look ugly and complicated because I wanted the graphs to look complicated, to illustrate the idea that asymptotic notation makes things look simpler. In this course, the running times that you'll be dealing with are all look like this. They will either be order 1, order log n, order n, order n log n, and order n squared. You might have one or two cases where you get something else, but most of the time, if you have something else coming out of your recurrence, it means you're doing it wrong. So nice tip to have. And you can see that I already started doing it. I'm already using O instead of theta. So I guess I'm getting into the habit.
So why did you leave the theta one blank for g of x?
Because whatever I put here is going to be wrong. If I put x to the power of 1/5, this is wrong because I can have an upper bound that has x to the power of 1/5 in it. But I can't have a lower bound like that because this function hits x to the power of 1/4 in infinitely many points. If I try to do x to the power of 1/4, same deal. Lower bound, yes. Upper bound, no. So whatever I put in here is going to be wrong. Thank you. Good question. Yes?
Is that 1.4 or 1/4?
1.4. They're 1.4 and 1.5.
Okay, because I thought you were saying 1/4, and then I was.
Oh, sorry, 1.4. 1.4. 1.4, 1.5. Okay, are we good so far? Okay, let's go through a couple of exercises. So I'll give you a few functions. Yes?
The omega, is that, it's a lower bound already without multiplying by any constant or something? Is that what it is?
So for all of these, what you put here is the simple form. So your lower bound can be this function multiplied by any constant factor.
So omega means lower bound?
Omega means lower bound. O means upper bound. Theta means both. Okay. Any other things to clear up before I ask questions? So it's your turn before it's my turn. All right, I'm going to go over a few functions, and I want you guys to tell me what's to help me write them in asymptotic notation. So I will have f of n, and I want to know its theta of what. So let's start with f of n equals 10 to the 80. Does anyone know why 10 to the 80? Yes?
Of 1.
Okay, that's the correct answer. You're going ahead though. I was wondering if you know why. Why did I choose this? Does anyone know why I chose this? Yes?
Is that what a Google is?
I think that's 100. You're getting close though. It's something. It's a really big number. All right, so it's a really big number. That's the estimated number of atoms in the universe. So realistically, any quantity that you deal with that will represent the real world is not going to be bigger than this. So if you want to get all philosophical, you can say that for any algorithm that you write and any realistic input, the running time will be theta of 1. But if you do this, we're not going to be happy with you on exams. So let's choose another one. 20n to the power of 7th. What's this in asymptotic notation and why? Yes?
Order O of n to 7.
Okay. Oh, that's the same thing. And to the 7. Thank you. Why is that?
Because if you distribute the exponent 7, 20 to the 7 is just a constant.
Excellent. 20 to the 7 times n to the 7. This is a constant, so it goes away. Okay. And before I do another one, I want to give you guys some help and remind you about logs. How many people remember the laws of working with logs from algebra or some math class? All right, you guys will be helping me write them for everyone else. So if I have log of n to the 100, and I want to get to the theta notation for it, what is it and why?
Log n.
Okay, excellent. Why is that the case?
That's equal to 100 log n.
Okay, so when I have an exponent here, I can pull it out in front of the log as a constant factor. So this is the same thing as 100 log n. Okay, now if I have a logarithm to the base using base 5 of n, how about this? Okay, so this is, can you say that again? Okay, so this is theta of log n because it is excellent. Log n over log 5. So exponents inside the logs turn into constant factors, bases turn into constant factors. So if you have an ugly expression inside the logarithm, you can most of the time simplify it to something really nice. And this contributes to the fact that these are the only functions that you will see when the answer is cleaned up in asymptotic notation. Okay, yes?
So when you're writing log, are you assuming a certain base then?
Yes, there is a certain base for logs. We're all computer scientists, right? So what's the natural base for our logarithms?
2e.
Okay, sweet. Math major?
No, I always heard natural base. And then
Okay, yeah,
natural-
it's a math joke. So for everyone else, a natural logarithm is in base e. For us CS people, a natural base is 2 because that's how many values you have for a bit. So log means log n is log base 2 of n. The good news is that most of the time we're working with asymptotic notation, so it doesn't really matter. We can communicate with our math friends and we don't have to talk about this. Okay, I need to get another complicated example. And my memory fails me. Okay. So log, see, I'm using ln to mean the math natural logarithm. So we still have that somewhere in here. Of log n to the base 100. They made me add all these parentheses in the last section to be clear, so I'm adding them now from the start. Who wants to help me clean this up? Yes?
log n.
All right. Wow, one step. Log n. Okay, can you tell me why very quickly?
So we can simplify out the base and the exponent in there.
Okay.
And then
Base goes out, exponent goes out.
log of something is another class complexity that's not exactly up there, but can
Yep.
be occasionally useful.
Yep. What does a theory student say when they're drowning? Log. Some of you are laughing already. You guys know this. Okay, what if I want to make this a little bit harder and I say log 5 of log n to the 100. You have to do a bit more work now. You can't just use the tricks on the right. Anyone else? Yes?
Still log n.
Okay, it is still log n, but for a different reason, right? Almost. Okay, maybe not. So the base still goes out just like before. But this guy now goes out here. So I will have this be sort of like, notice that I'm not saying equal. I'm saying like because I got rid of the base. So it's like 100 times log n, which is log 100 plus log n. And this is a constant factor. This grows as n grows. So this is going to become incredibly small as n becomes larger and larger, so I can get rid of it. Okay? Okay, one more, and this one's gonna be less boring.
Spit it out into a separate term. The log of 100. Going from the last step, how are you able to pop it out?
If my memory works, I think log of AB is log A plus log B. Am I right, guys? Sweet. Good question. I wasn't sure, but now that you asked, everyone else helped me make sure it's right. Okay, I'm erasing so much because we're going to need more room for this. So I have a log again, but this time what I have inside the log is n choose n over 2. Does any brave soul want to come up here and solve this for me? No? You guys are going to make me write for the entire hour? I'll offer help.
What's n choose n?
So this is...
Is that n factorial over
Yep.
n divided by 2 factorial?
N factorial over n divided by 2 factorial times n divided by 2 factorial. Close. And I'll give out another hint, which is that n factorial can be approximated as square root of 2 pi n multiplied by n over e divided by n to the power of n. But I think this will make you guys not want to come up and solve this. Yes? I was... is that it? Is that not it? Did I get it wrong? Okay, I think that's in asymptotic. That's what I think we'll get to that. But factorials grow exponentially. So it should be something like this. Okay, so we have that nice approximation. Does anyone want to work it out, or will I have to do it? Keep that in mind when I'm grading your homework. Okay, so it's log of square root 2 pi n multiplied by n over e to the power of n. I'm going to put these two together. So 2 pi n over, there's an n over 2 there, right? So it's n over 2e times n over 2 to the power of 2. Okay, I can get rid of this guy because it's a constant. I can get... No, I can't get rid of this guy yet.
The denominator should be 2 pi n over 2 under the radical. So it's just
Yep. 2 pi n over 2, so this simplifies. Okay, thank you.
You can square the bottom term and get rid of the square root in the and just make
Yep.
it the nth power and then cancel the some of the exponents.
Okay, do you want to come help me?
Sure.
Thanks so much.
Okay, so we can distribute this exponent here to cancel this, and then we get a square root of pi n times n over 2 e to the n. Sorry about my handwriting.
I think it's better than mine by quite a bit.
Square root of pi n, oops, and this is square root squared, so that cancels. Times n over n.
Do you need
Since-
parentheses or n over 2e?
Yeah, that's probably good. So since this is n over e to the n and n over 2e to the n, well, since they're to the n, both the n, we can keep them as a single exponent and cancel stuff, so we just get square root of pi n to the times 2 to the n over pi n. Can do some more canceling and just get 2 to the n over. I'm going to simplify this 2 to the n over the square root of n. We can take out the pi because it's in a natural logarithm and it's a constant factor. And this is log of and then since it's a log of, it's just a log of 2 to the n, so it's since it's log, you can take out, you can turn it into log of 2 to the n minus log of square root of n. Log of 2 to the n is a much greater complexity than square root of n, so we can.
Sweet, thank you. So see, complicated formula, even more complicated formula came out to be one of the numbers that I promised it would come out to. Thanks for the help. So you can get rid of the pi as soon as you want to, and this is the last step. I just want to say it again to make sure everyone heard it. So once you get here, you get this, order n minus log of square root of n, which is this is order n minus 1/2 log n, and the log n is much smaller than n, so this goes away completely, and you get this as your final answer. Okay, does this make sense? Any questions? Anyone? How many people are still paying attention, honestly? Wow, nice. You should come to all my sections. Okay, let's talk about something we covered in class. Let's talk about peak finding. And we'll start with 1D peak finding, and then we'll go to 2D peak finding. So does anyone remember the pseudocode for the faster 1D peak finding by any chance? 1D peak finding. I think everyone said they went to lecture, so I don't have to explain what peak finding is, right? Okay, let's go for it. So suppose I have a few numbers. 3, let me write this. 3, 4, 5, 6, 7, 6, 5, 4. So the peak finding problem says there's an array of numbers, and I want to find the local peak. And the local peak is a number that's surrounded by numbers that are smaller or equal to it. So there shouldn't be any larger numbers than it. And I want to find a peak as quickly as I can. So what's the faster algorithm that we talked about in lecture? Yes? Okay, you didn't answer, right? As much, at least so. Yeah.
Binary search.
Okay, it's exactly like binary search. Yep. Do you want to help me write the pseudocode? You can tell me what it is.
Sure. So I guess start in the middle.
Okay. Start in the middle. If you write this on your pset, you might want to be a little bit more formal. Someone asked me about proofs. I would say something like start by looking at the middle element of the array. Same thing though. Okay. So let's pretend this is the middle. Now it is. What do I do?
So then you can check one side of the middle. So say the right side.
Okay, I'm looking at the right side. I see a 7 there, so I know for sure that this is not a local peak, right? What do I do now?
So now you can start over using 7.
Okay. What if this would be small? What if I would look at 5 first? Or should I look at the other side too?
Well, you don't have to in this case, but if 7 were smaller, then you would go and look at the other side to check to see if 5 was also smaller. In that case, you've already found it.
Okay. So I have to look at both sides and make sure if none of them is smaller, then if none of them is bigger, I found a peak. If any of them is bigger, then I can go whichever way I want. So I saw my 7. I'm going to cut this in half, and now I look at this, you're saying, right? So look at neighbors. By the way, can anyone understand my handwriting? Is it even worth bothering to write? Okay. I see 3 nods. I'm going to write for those 3 people. Look at.
Cursive about 12 years, so.
Okay. Thanks. Not feeling old at all. Okay, look at neighbors. Figure out if you're a peak. You're one of the people that said you can read it. So now there's only 2 people that can read my handwriting and that I like. Look at the neighbors. See if local peak. And if not, figure out which way to go in. And I'll say if not, recurse. So what's the running time for this? Suppose I have n elements to start with. That's my array size. I will use t of n as my running time. So to figure out the running time for the whole algorithm, I have to look at the running time for each step and add them up, right? What's the running time for the first step? Look in the middle. One. I would not say it's 0. I still have to look at it. Or to be on the safe side, you say 1, theta of 1. It's a constant. Okay, now I have to look at the neighbors, and I have to see if one of them is bigger or not. How about that? How much time is that? I heard the constant. Okay. Very soft voice, but I heard a constant there, so I'm going to take it. So this guy is a constant. If it's a local peak, I'm done. If it's not a local peak, what's the running time for this?
And over 2 since before the one that you divided by 2, correct?
Yep. So I'm looking at this guy. It's clearly not a peak. So I'm going to look in the right side because I see a 7 here that's bigger than a 6. So now I have the same problem, except my array size just dropped to half. So same problem because I already have a name for it, except the input size is different. So the running time for this entire step is theta of 1 plus t of n over 2. So the running time for the whole thing is, I should have said theta of 1 here, sorry. So theta of 1 plus theta of 1 plus t of n over 2. So this is theta of 1 plus t of n over 2. So I wrote out my pseudocode, looked at the running time for each step, added them up. Now I have a recurrence, and I have to solve it. Let's solve it. We sort of glossed over that in lectures, so we're going to do it now. So t of n equals theta of 1 plus t of n over 2. I'm going to expand this using the definition. And theta of 1 is long, so I'm going to call this c instead. It's a constant, right? So c plus, expanding this, c plus t of n over 4. I'm going to expand it again. And again. Anyone getting bored of this? So if I expand it a lot of times, I'm going to get I times c plus t of n divided by 2 to the I. And you can expand it as many times as you want until you see the pattern. But this is the pattern. So I have a recurrence. What else do I need in order to get a function? I need a base case. So the problem size gets smaller and smaller and smaller, but at some point it becomes so small that I can solve it just by looking at it. What's that case? Okay, so if I have an array of one element, it's a peak, right? Job done. So t of 1 is a constant. So I want to write this in such a way that this becomes this. So I want to figure out an I such that t of n divided by 2 to the I equals t of 1. And the easiest way of doing that is to say that n divided by 2 to the I is 1. So I is the inverse of an exponential. Anyone? Logarithm, thank you. Log n. So I have I, and I'm going to plug it back in here. And I get constant times log n plus t of 1, which I know is theta of 1. I'm going to make this theta of 1 again. So theta of 1 times log n plus theta of 1. And I know that log n dominates a constant, so this is going to be theta of log n. Solved. Okay, how are we doing? Yes?
In the second to last from the bottom, I don't understand after the c times log n. Replace I by log n, and the second part of the equation, how did you...
Okay, so in the jump from here to here where I set I equals log n, right?
Yep.
Okay, so I becomes log n, c stays c. You're wondering about this part, right? So if I is log n, then 2 to the I is n. So I have t of 1, which I have here. So I wanted to have this happen. When I was solving for I here, I set this guy to my base case so that I can get this to happen. The idea here is that you're expanding the recursion forever, and you know that at some point you're going to have to stop. When do you stop? You stop at the base case. So you force this to become the base case. Okay? Okay. Let's do 2D peak finding. Let's talk about it a little bit. So 2D peak finding is exactly like 1D peak finding, except you have a 2D matrix instead of a 1D array. Let's see if I can do this right. So suppose this is our matrix, and suppose these are the rows. Suppose we have m rows and n columns. Can anyone remind me what's the pseudocode for 2D peak finding that we talked about in lecture? So we had 2 attempts. The first one was a clear failure. It didn't work. The second one worked, and we talked about its running time a little bit. And then Srini asked you to think of a variation to the second one. So let's do the straight up second version of the pseudocode without the variation. So 2D peak finding. What's the algorithm? All right, one person was not asleep in my section at the end of lecture. I'm proud.
Okay, which one of us will split at the same time?
You had your hand up first, so.
So you just pick a middle of the column,
Okay.
and then you find a peak there,
And
and then check the neighbors, I think.
find peak. Neighbors.
Neighbors in the same row?
Yeah, sorry.
Row is the horizontal one, right? Okay. So what do you mean by find a peak here?
Like within the column?
Yes. So find the peak using what we talked about before?
Yeah.
Okay. Find 1D peak. So you're thinking ahead, you're thinking of the variation that Srini asked you guys to think about at home. I'm glad you thought about it, that's good. But what's the one that we had in lecture? I don't want to give you guys the answer yet. So what did we say we're going to do in lecture? Yes?
I think we just picked a spot, checked the neighbors, and kept walking uphill, if that makes sense. Every time we found a neighbor that was bigger, we moved to that spot, checked its neighbors.
So this is the first algorithm that's slow. It works. You're going to get the correct answer. But it's slow because if you have some handily crafted matrix, you can go like this, and you're basically going through the whole matrix. Yes?
I think the second algorithm was find look through the column for its maximum and then look to either side.
Okay. So instead of finding a 1D peak, we're going to find the maximum value. Okay, and this is correct. And let's look at its running time. Does anyone want to help me? So this is T of n m, right? N rows, m columns. So what's the running time for the first step? Come on, this is the easy one. Yes? It's a constant. Perfect. Okay. What's the running time for finding a maximum out of n numbers? Okay. Perfect. And suppose we do that here. Suppose these rows don't exist. Suppose this is my entire matrix. And I'm here, and I found a maximum. What do? I look left, I look right. If both of them are smaller, then it means I found my peak, because I know that number was a maximum in my column. Now, if that's not the case, if I find a number that's bigger, I'll go in that direction. Does that sound reasonable? Okay, so maximum for my column, and I'm going to go right. So check neighbors, and I have the same 2 conditions there. If it's a peak, then I'm happy. Otherwise, recurse. So what's the running time if I have to recurse? How does the new problem look like? It's an identical problem. I still have a matrix, except what changed? So suppose I got here, and this is the middle of my matrix, and I see that this guy is bigger. So I'm going to recurse to the right side. What happened to my problem size? Okay.
Sorry, I'm not answering your question, but shouldn't phi max be theta of m, not n? Or is that an
Let
m?
me see.
I can't tell.
You are right. Thank you for paying attention. Theta m. Sweet. That would have tripped me out later. Thanks for saving me.
Okay, so what was your question? Sorry.
So the question is, if I have to recurse,
Uh-huh.
what's the running time? So if I have to recurse, I'm in this array that was originally n by m, and I'm only going to look at the right side. How many rows do I have in the new array? Start with the easy one. All right, same as before. How many columns? N over 2. Sweet. So the recursion for this is theta of 1 plus theta of m plus t of n over 2 and m. I know that a constant can be absorbed by this other guy, so it's theta of m plus t of n over 2 m. How would I solve this? What's the first thing that we need? Yes?
You need to figure out the base case.
All right, excellent. Base case. What's the base case?
T of 1 comma g of n m, sorry,
Nice.
equal to O of m.
Okay. Sweet. So if I only have one column, then I can find the maximum, and I know for sure that's going to be a peak. Job done. That's my base case. So I'm going to reduce the problem size in half until I get to a single column. Then I find the peak there, and I'm happy. How would I solve this recurrence? It's a 1 minute answer because I think that's exactly how much time we have as a hint. Come on, guys, this looks familiar. Yes?
It's like the recurrence over there.
Exactly.
With this function of just n.
Exactly. M never changes, right? So this is basically a function of n. So if m never changes and I pretend that it's a constant, this looks exactly like the recurrence that we solved before. T of n is a constant plus T of n over 2. So I'm going to get that constant multiplied by log n, which is the solution that I had before. So the running time is theta of m log n. All right, I think I have 30 seconds. So what if I would try to do this algorithm instead? It's another 1 minute question. So I guess I'm cheating. I'm taking time away. Sorry. So what if I would be finding a 1D peak instead of finding a maximum? I'm looking at the running time because if the running time is going to be the same, it's not even worth thinking if it's correct or not. If it's a more complicated algorithm with the same running time, why care about it? So is the running time going to be better? Okay, I heard a nod. Why?
Won't it be log m times log n?
All right, so 1D peak is exactly what we had there. Thank you. 1D peak is exactly like you said, log m. So this constant here becomes this constant here, so the algorithm would be a lot faster. As an order of magnitude idea, if your m and n are 1 million each, then log n is 20. So that's a 50 times x improvement. And these are real input sizes you might get. And that's it. Thank you, guys.